Go team. Okay, so we're trying to find size, we're trying to find the coefficients Ca and Cb. And to do that, we're going to take the expectation value of the energy. So when you take this and you put it in to here, you get these wave functions. Go team, you got a lot of them. And when you break them all up. And so what you end up having, this is I'm gonna name this alpha A. This one I'm gonna name, alpha B. This one I'm gonna name beta. And this one I'm gonna name beta. Okay? And by the way, I'm following exactly the notation and Atkins 10.4 or 9C or 9D is what I'm in. Anyway, so the way that we do this is we set up a series of equations and we solve for the coefficients. And so I want to say that psi A, or alpha A minus E is multiplied by Ca plus beta minus ES CB is equal to 0. Okay, so where did this come from? Well, and this is something that would be really good for you to follow on your own in Atkins and see if you can figure out where this comes from. I'm going to give you the verbal description. When you take this, you're going to have, and you have Ca and Cb put in to each of these, or this whole thing put into this equation, you're going to find that there's going to be some Cas and Cbs throughout this. I should say that is not equal to this. I'm just breaking them up into 4 different parts because you're going to have some plus signs here. When you do that, you're going to have all of these are going to be equal to some sort of E psi, such that you have H psi equals E psi. Okay, so then you can factor out that E. Cool. And then what you can do is you can set those equal to 0, and then you can get beta minus ES Ca plus alpha B minus E CB, and that equals 0. So from here, what you can do is set up a secular determinant. Now, this is the same mathematics that was used with the Pauli exclusion. So determinant to find E. Go team. Okay, so the way that you set that up is you're going to do a matrix where you say, all right, alpha A minus E, alpha B minus E, beta minus ES, beta minus ES, that equals 0. You cross multiply and you solve for E. So you'll get alpha A minus E times alpha B minus E minus beta minus ES. Luckily that's squared. Then all that equals 0. Solve for E. Awesome. Go team. I'm going to pause. I'm going to erase. There you go. You can pause and look at that if you want. And then I'm going to solve for E using that equation. Ta-da! That was easy. This is some of the easiest lecturing I've ever done. I'm just going to write the equations up and be like, see, it's that simple. Holy crap, that's complicated. Okay, look at what this means. You've got energy plus minus. Okay, so you've got the constructive interference and you've got the destructive interference because now we're talking about molecular orbital overlap. You've got alpha A plus alpha B, alpha A minus alpha B, and then you've got 2 beta divided by the difference here squared, all raised to the 1/2. This is a lot. But let's think about what these mean. What is alpha A? That equals psi A Hamiltonian psi A d tau. What is that? That is the expectation value of the total energy of just psi A. That is the atomic orbital energy. Okay? So that's the atomic orbital energy of A. That's the atomic orbital energy of B. All of that plus or minus the difference in the atomic orbital energy. So if you want to have the highest energy, you are going to have, so the highest energy constructive interference, you want this number to be big or small. Well, if you want, this is going to be in the denominator. So, and what is beta? Beta is called the resonance orbital, by the way. The resonance integral. And alpha is called the Coulomb integral. But here we've got psi A H psi B d tau. Okay, so this is the total energy operator. So this would be the expectation value of the overlap of A and B. So if this is large, then you're going to have this squared, of course, square root that. But what you're going to want to do is have the most similar values here. So if this is a large number, that's going to be small. So sorry, if this is a large number, as in there's a great difference between the energy of A and the energy of B, this is going to be a small number, and this is going to be a big number. Okay, so you don't want that. You want the difference here to be really small. Okay, so that this practically goes to zero, and what you're left with is a maximized value there. And if you think about what that means, you want the energies of A and B to be similar for the most stable energy. So the strongest bonding occurs when the contributing orbitals have the most similar energy. And if you think about it, the strongest bonds are going to be the diatomic homonuclear. And so if you can make the homonuclear or the heteronuclear as close to homonuclear, you're in much better shape to have a stronger bond, i.e. a lower energy state. Go team. Cool. Ta-da, heteronuclear. That's, oh, by the way, one more thing. There's the Mulliken and the Pauling electronegativity scales. Those are great. They're empirical. Hooray. Well, not really empirical, but they're based off ionization energy is the Mulliken one, and then based off the resonance energy, which is the Pauling one. I really don't go into those, so maybe I'll do a podcast on them. We'll see. Be well, everyone. One more look.